Okay, when we make enolates, we must pay attention to the bases. So let's talk about what base we use to make an enolate. I'm going to put them in two boxes, strong and weak. So let's look at weak first. Okay, so let's draw a ketone again. Again, we'll just keep it simple. We'll draw acetone, but don't be bothered by this. We could do any ketone, but acetone makes it quick and easy to draw on the screen. So here's our ketone. Our weak base is going to be sodium hydroxide. Now you might be surprised at this. But Dr. Stevens, sodium hydroxide is a pretty strong base. It is a strong base if you're confined to the world of water. And as organic chemists, we do things not in water. So actually, in the big picture, sodium hydroxide is not a super strong base. I'll grant you, in general chemistry, it is a strong base. But for us, it's a fairly weak base, maybe a moderate base. So as a base, we know, as an acid, we know a ketone has a pKa of about 20. This is our acid. It's going to react with our base. We're going to have some kind of acid-base equilibrium. We're going to form our enolate. And when I draw the enolates, even though the better resonance form, the major contributor, is where we have the charge on the oxygen, since reactivity-wise it always reacts through the carbon, I'm going to keep it as a carbanion. You'll see people treat those differently. The enolate is the conjugate base. So what is the conjugate acid? The conjugate acid of hydroxide is water. So what's the pKa of water? pKa of water is about 16. So this is the stronger acid. Over here, the ketone is the weaker acid. So what do we notice about this equilibrium? Acid-base reactions go from strong to weak. So therefore, our equilibrium favors the starting materials as drawn, the left-hand side of the screen. And in fact, a difference of a pKa of about 4 units is about a factor of 10,000. So we would expect this reaction to give us about 10,000 parts of our hydroxide and 1 part of our enolate. However, sometimes we just need to form a tiny bit of enolate. And by forming a bit of enolate, as long as we get this to react, this equilibrium by Le Chatelier's principle shifts to form more enolate, which then reacts and continues to shift. So sometimes a weak base is just fine for making enolates. We'll have to define when those are. But anyway, sodium hydroxide is an okay base. And in the same box as sodium hydroxide, I would put things like sodium methoxide, sodium ethoxide, all the alkoxides, not just sodium hydroxide. Okay, now let's talk about relatively strong bases. So again, here's our ketone. Now, how can we make a base stronger? Well, one way to make a base stronger is to put the negative charge on a less electronegative atom. What's less electronegative than oxygen? Nitrogen. So we're going to use an N- base, and the classic one to use is this one. This is called LDA, or lithium diisopropyl amide. So this is actually a super strong base. Our acid over here, our ketone, is about the same, pKa 20. So now we're going to strike up an acid-base equilibrium. Let's draw in our alpha hydrogen next to our carbonyl. And we're once again going to form an enolate. I'm drawing the carbanion resonance form. What is our conjugate acid? Our conjugate acid is this now protonated amine. It has a pKa of about 35. Okay, so now when we look at these, which is a stronger acid, the pKa 20 or 35? Well, this is our stronger acid. This is our weaker acid. What's the direction of the equilibrium? Acid-base reactions go from strong to weak. So this equilibrium goes super strongly this way. In fact, the difference of pKa, this is about a 10 to the 15th. K is going to be around 10 to the 15th because we have a 15 difference in 15 pKa units. Up at this top reaction, the K was more like 10 to the minus fourth. Because we have a difference in 4 going the other way in our pKa's. So here are the two bases that we will typically use, either sodium hydroxide or the alkoxides, methoxide, ethoxide, or we'll use LDA. And which one we use will depend on what type of reaction we're doing, but both can work and be used to form enolates.